remember binary star systems? I mean, not exactly like the twin suns that illuminate the desert planet of Tatooine in the world of Star Wars, but kind of like the twin suns that illuminate the desert planet of Tatooine in the world of Star Wars. Really, I mean these types of binary star systems, with two stars orbiting a common center of mass. Now, whether or not they have planets orbiting one or the other, or both, is irrelevant at the moment, since we're primarily focusing on the two stars themselves. In most cases, the stars orbiting each other will have different timescales of evolution, with one evolving faster than the other. So much so that if the aging, expanding star expands so far out that its outermost layers of gases go past a certain distance, they'll start to interact with the companion star in the binary system, getting pulled more and more towards it because of the star's gravity. These points of no return for the runaway matter from a growing star occur at what's called a Lagrange point, where the gravity from the object on one side balances the gravity from the object on the other side. So really, any object that's located at the Lagrange point between two masses will kind of just be floating there. But the extent of the gravitational pull of each individual star is limited to what we call the star's Roche lobe, the size of which is determined by the Roche limit. Now, what exactly is the Roche limit, you may ask? Well, our trusty friends at Wikipedia define it as the distance from a celestial body within which a second celestial body held together only by its own force of gravity will disintegrate because the first body's tidal forces exceed the second body's gravitational self-attraction. Got it? No? Well, don't worry. Because in other words, we can define the Roche limit as the shortest distance from a star at which a second object, whether it's a star or a planet, an asteroid, whatever, can be held together by its own gravitational forces without falling apart. So in the case of a detached binary, each star is contained well within its respective Roche lobe. But when one of those two stars evolves and expands, it fills its entire Roche lobe, coming into contact with that Lagrange point between the two stars. This scenario creates a semi-detached binary system. And in one of these binary systems, a stream of mass begins to transfer from one star to the other. It may also happen that the two stars begin to share a common envelope of mass, with the two distinct cores of the pre-evolved stars still in place in the midst of this star soup in what's called a contact binary. But the particular case that we'll be focusing on for the remainder of the video is the semi-detached binary. Primarily one in which the physically smaller star is a white dwarf, and the larger of the two is a star in the late stages of evolution. This creates the ideal conditions to lead to a nova. But what are novae? Well, first off, it's the plural form of the Latin word for new, because from our point of view, a nova is the sudden brightening of a star followed by gradual decline in brightness. So for ancient astronomers, it appeared as though these novae were new stars, when in reality they weren't. The physical process that actually leads to a nova event begins with, like we said, a close semi-detached binary star system where one of the two stars is a white dwarf. Hydrogen from the outer shell of that expanding companion star is transferred to the white dwarf, forming a dense layer around that star. As time passes and more material continues packing onto the white dwarf, that layer gets compressed and heats up as a result. When the temperature of that outer layer reaches 10 million Kelvin, the temperature necessary for hydrogen fusion, the entire layer of hydrogen ignites explosively. And this explosion is the nova, and we generally see 2 or 3 of them in our galaxy each year. In a nova event, the white dwarf remains intact after the hydrogen layer accumulating above it ignited and exploded. And that is the main difference between a nova and a Type 1a supernova. In a Type 1a supernova, again we're dealing with an accreting white dwarf in a binary star system, just as before. But whereas a nova blast just removes the built-up hydrogen, a Type 1a supernova not only removes the built-up hydrogen layer around the white dwarf, but it completely obliterates the white dwarf itself. Now this is because the white dwarf that's associated with these Type 1a supernovae are much larger than those involved in novae, since they came from stars that were originally 8 solar masses or higher when the stars were in their main sequence phase. With the white dwarf already having so much more mass in this case, the accreted layers of mass on the white dwarf get so hot that they reach the necessary temperature to ignite carbon fusion as well as hydrogen fusion. It's the onset of the carbon fusion in the core that kills the white dwarf in this blast by causing a runaway process that rips the star apart in an explosive supernova. Here we can see the light curves of type 1a and type 2 supernovae, where we have luminosity on the vertical axis and time on the horizontal axis. We can also see that in both cases, the sudden increase in brightness is recorded both before it reaches the peak and well after it dims down over time. A type 1a supernova will always have an absolute magnitude of -19, and this is because the physical mechanisms leading to this event will always be the same, so regardless of where the type 1a supernova happens, it's going to have the exact same brightness each time. With absolute magnitudes always at -19, type 1a supernovae can be seen from great distances, further than even the Cepheid variables or type 2 supernovae that we covered earlier. For this reason, type 1a supernovae are another great example of standard candles in astronomy, since they'll always have the same absolute magnitude no matter what. And this can be used to help determine distances.